So today we're going to talk about the topic of buoyancy. This is still a topic in hydrostatics because the fluids we're going to be dealing with are still not moving. So let's see what's going on with buoyancy here. But first, let's stop to think here. So here we have a figure where I accidentally put the figure in slightly tilted. So A and B are actually level with each other. But how does the pressure at point A and point B compare? And explain. Well, hopefully you said that assuming that this fluid, this salt water, is not accelerating, assuming it's, let's say it's assuming it's still, then the pressures at those 2 points are the same because they are at equal depth below the surface of the fluid. Alright, so let's talk about buoyancy. Alright, so you've maybe experienced the buoyant force before. Well, actually you're always experiencing it because you're always in a fluid. Right now you're in the fluid of the air around you. But you might be more familiar with it when you're, like, say, swimming in the pool or swimming in the sea. Right? You feel like you're floating in that water. Right? So this kind of floating feeling, this is due to the buoyant force. So the buoyant force is the upward force due to a fluid. Right? So why does this happen? Well, we know from hydrostatics that as you go further down in a fluid, the larger the pressure becomes. So let's say we have some sort of cylinder in here, a liquid fluid, let's say water. This cylinder, if we're comparing the pressures, well, we've got the pressure at the top of the cylinder and the pressure at the bottom of the cylinder, where the pressure is greater at the bottom. We also have pressure all around the sides of the fluid, or excuse me, of the cylinder here. But the forces associated with those will all cancel out because they're dealing with a symmetric shape here. Anyway, so the pressure above is smaller than the pressure below. Well, since that circular area of the cylinder is the same, then since pressure is force over area, this means that the pressure on the lower end of the cylinder is larger than the upper end, and therefore we have a net force upward. And this net force upward is what we call the buoyant force. So it's basically the buoyant force due to it's a force due to the difference in pressures acting on an object. So let's see. So something else I want to bring up here. Now, when an object is submerged or immersed in a fluid, it displaces that fluid. Right? And the amount that fluid that's displaced is equal to the volume of the object or the portion of that object that's submerged or immersed in the fluid. Right? So here in this picture, the volume of the fluid displaced is equal to the volume of the cylinder. Where if this cylinder was just kind of floating on top of the water, only part of that cylinder would be underneath the water, and therefore the volume of the amount of the cylinder under the water is going to be the amount of fluid displaced. Okay. A lot of words for kind of a simple thing to say. So let's talk about Archimedes' principle. All right. If you don't know much about Archimedes, he's brilliant. I recommend reading up on him. He's pretty interesting. But Archimedes came up with this idea, or this, I guess it's more of a postulate here, but a fluid exerts an upward buoyant force on an object immersed in or floating on a fluid. So he basically came up with the idea of buoyancy. At least that's my understanding. I could be wrong about that. I'm not super well versed in the history of physics. Anyway, what is very profound is that he determined that the magnitude of this buoyant force is going to be equal to the weight of the fluid displaced of the object. So this means we can have a formula for the buoyant force. So we're seeing here that buoyant force is equal to weight, but it's equal to the weight of the fluid displaced. So weight, has the formula simply of just mg. So the m we're dealing with here, though, is the mass of the fluid displaced, not the mass of the object. So using our density formula, we could then say that our buoyant force is equal to the density of the fluid displaced and the volume times the volume of the fluid displaced times g. All right. So just be careful because your formula sheet just simply has this equation as written. I'm pretty sure I actually just snipped an image from your formula sheet and pasted it here. they do not put a subscript on density. You have to remember that the density here is the density of the fluid. The volume is the volume of the fluid displaced. All right, so just be very careful for that. It's a very easy, simple mistake to make to accidentally use the object rather than the fluid. All right, so how can we determine if an object is floating or sinking, or kind of what's the physics behind that? All right, so we can look at what's going on with the buoyant force and compared to the object's weight. Right? So if an object, let's say, is completely submerged in water, right, we've got an upward buoyant force and a downward gravity force. And actually, that's going to be the case if it's not completely submerged in a fluid as well. But here, let me actually just go to the next slide for a moment here. If we're looking at these forces, we see an object's going to, let me take up this moment here. The titles here, sinking, floating, neutral buoyancy, I'm not a huge fan of them. So our first situation, we have an object accelerating downward in the fluid. And that's when the object's weight is larger than the buoyant force. Our second situation here is the object accelerating upward in the fluid. In this case, then now our buoyant force is larger than the weight of the object. And the last situation is going to be object having a neutral buoyancy, which a lot of times the word floating is associated with that. That's why I'm not really a big fan of these titles. But in this situation, if the object is not accelerating in the fluid, then the buoyant force would then be equal to the weight. We can compare this to what's going on with densities, and in fact, you've probably learned about this in a previous, maybe in chemistry class, possibly bio, or maybe middle school science. But you can basically learn things about an object's density, or more particularly its average density based on this, right? And we go back to the previous slide a moment, and that has to do with the fact that an object's average density is going to be its mass divided by volumes. Then we compare what's going on with forces here, and kind of long story short, if the object's average density is less than or greater than the density of the fluid, it's going to sink. If it's smaller, then it's going to accelerate upward in the fluid. But if the average density of the object is equal to the fluid, then it's going to have a neutral buoyancy. So meaning it's just it floats there. So actually, fish use this to their advantage, right? So fish have something called the swim bladder, and while I'm not well versed in the biology behind how a swim bladder works, but basically they can fill and reduce that swim bladder to then increase and decrease their average density, which causes them to rise and lower in the water without having to actively swim with muscles and propel themselves. Right? So I find that pretty interesting. All right, so quick question for you. Which do you think is true? Which is more dense, iron or mercury? Well, let's look at a little video here. Don't try this in real life. All right, so we've got liquid mercury here, and we have an iron anvil. All right, and as you'll see, so this person is placing it in the mercury, and the anvil floats. All right, so since the anvil is floating, then we see then that the fluid must have a larger density. So mercury is more dense than iron. So let's stop to think here. So let's suppose we have a block of iron sinking to the bottom of a vessel of water, while a block of wood of the same size floats in the middle of the vessel. Right? So both these objects are completely submerged in the fluid of water. On which is the buoyant force greater? The answer is that the buoyant force is equal on both. Because they're both completely submerged, and they're the same size, the volume of the fluid, being water, is the same. The volume of the fluid displaced, excuse me. So therefore the buoyant force must be the same. It does not matter the density of the object. Remember, it's the density and volume of the fluid displaced. All right. So kind of the last thing I want to touch upon here is kind of what goes on with boats and balloons in terms of them. We'll use the word floating. Well, let's suppose we have a chunk of steel, right? If you put a chunk of steel in water, it's going to sink, right? Well, boats are predominantly made of chunks of steel, so how can they float? Right? So the trick here is we're dealing with this idea of the average density. So when you're dealing with the boat, what's important is the part of the boat that's below water is not just steel. There's also, we'll go with the idea of air, right? We'll imagine that we have a completely empty boat. So the density of the object we're dealing with here is not just completely just steel. It's a lot a lot smaller than the density of, I guess lesser is the correct number. Wow. Anyway, what was I trying to say? Anyway, the boat will become neutrally buoyant when the weight of the boat is going to equal to the weight of the fluid displaced, being, if you kind of look at this image here, once it reaches a certain depth, the way the boat's constructed, that amount of, the weight of the water is going to equal to the weight of the boat. So the same idea here can be applied to balloons. So the last thing I want to ask you, it's actually a pretty interesting question. So let's suppose we have an ice cube that floats in a glass of water and it's filled entirely to the brim. When the ice cube melts, will the water level fall, stay the same, or rise? What do you think? And also explain your reasoning. So it's actually going to stay the same. So the reason for this is that the weight of the displaced water by the ice is going to be equal to the weight of the ice cube. So when the ice cube melts and turns into water, the amount of water will exactly fill the volume that the ice cube is now displacing. All right. I'm not going to ask you that last question, but you can think about it. Let me actually show you. If you want a little bit more of a rigorous explanation here, this links to the physics stack exchange. Can I move this? Can't move my screen right now. Okay. Well, so there's a person here that answered this question in a lot more detail. So they go into the math behind it. I will try to link this article somewhere that you can find pretty easily. With our homework, the math here is very interesting. They do a very nice job explaining it. All right. But anyway, I just kind of skimmed through if you want to stop and pause too. All right. So anyway, thanks for listening.